Okay, now on to the simulation itself. So we spent all that time creating this density volume, and I'm actually going to turn these lights and camera off so we can see a little bit easier. This is going to be the density that we source into a simulation, and I think that for our little example here, we'll have it maybe dissipate out a little bit, disappear a little, like evaporate into the air a little bit, and have some turbulence kick it around in some interesting ways. So given that this is going to be the source, I'm just going to rename it source now. Press enter to dive in. I'm going to make a null SOP. Just call it out. And that's just a good practice so that we can have the simulation point to this out and always know that we're getting the end result here, rather than have it point to this and source this in, but then, oh, later we wanted it to do more density, but the simulation still pointed to this one, so we didn't get this. So we just point to this guy and be sure that whatever I do in here, we'll pick it up later. So turn that off. And one more little bit of housekeeping is we don't spend much time in the menus up here, but there's the hip file options. Just make sure you're aware of what the scale of the scene is. You can see unit length is 1 meter. Our pig head is apparently, by middle clicking, 2.1 meters wide, and so on and so forth. So just be aware, it's pretty big for a pig head. It's more like a cloud in the shape of a pig head. That's going to matter because the simulation, they're usually driven to work in real world units. So the kinds of effect that you're going to get are going to be directly tied to the scale of your scene and the objects that are in it. So anyway, we type tab DOP network. There it is. And just as all of these items are SOPs, surface operators, not literally that they are working on a surface. There's no surface here as a fog. But the surface operators are really any of these geometry-minded items that build up geometry in the scene. Whereas in here, we're going to have DOPs. And these are going to be dynamics operators. So let's look at the DOP net. There's a few interesting things here. One is start frame. Now, we're starting on frame 1. A lot of times in production, you could start at any frame. Maybe a meteor hits the ground on frame 30, and you might have to change it to 30 or what have you. And you'll see that it'll change the offset time with it. These green fields, of course, mean that there are expressions on them already. The time step in particular, if we need more subframes, if we need a more accurate solve, but instead of telling our simulation to work the solution out, meaning to solve, instead of having it to solve every frame, we might need it to solve twice per frame. So even though we only see the result once per frame, it might need to do several sub-frame solves. And you can see how the time step is getting smaller and smaller every time. So as you can imagine, this will dramatically increase your simulation time. Definitely keep it at 1 to start. You may never even have to move off of 1. But if there's going to be quick movements, you're definitely going to need to kick it up to maybe 2 or 3. Try not to go over 4 or 5 if you can help it. And definitely, again, start at 1. So 1 is fine and 1 is fine. So we jump in and let's create some DOPs. The main ones you're going to need is a smoke object. And we already actually get this output DOP for free down here. Meaning, once again, that this is the end result of the sim. Whatever stream leads down to here is the end result of the sim. Now, unlike in SOPs, and I'm going to bring the SOPs up over here, with the SOPs, you are getting the entire bit of geometry is passed to node, from node to node to node, making small or big changes to it, and then ending in some result here. What you're charting out in DOPs is you're saying these are relationships. So by creating a pyro solver, meaning the actual simulation algorithm that will solve our smoke every frame, at its most basic, the solver will take the density and move it along. I can't select it for some reason. It will move it along based on the velocities in the scene, or in our little container here, to result in the new positions of the smoke. So the turbulence will cause velocity. The smoke itself will come from over here, and you're about to see how that goes. So let's bring that smoke into our scene. On the DOP object itself, this node is going to create in the simulation a DOP object. It's called Smoke Object 1. It's called Smoke Object 1, not actually because we typed it here, but because under this tab, the object name is $OS, which means object string. It means it's a variable that will evaluate to whatever text is here. So if that's a little confusing, I could type Steve here, and the object will be called Steve. So you can see it's not called this just because this is typed here. It was only called that because OS is a nice way to only have to update one of these things. And now you can see it's back to being smoke object 1. So what is a DOP object? A DOP object is a container. And in fact, all DOP objects, if we dive in, are built on an empty object. They start out as and they have a nice little image here. It's a little cube. It's an empty cube. It has nothing in it. And we're going to put stuff in it. We're going to put densities in it. We're going to put velocities in it. We might even put temperature inside of it, or all kinds of fun things. For now, it's a literal container in 3D space, as you can see. And it'll also be a metaphorical object in that it will store the information that the solver craves so badly. And again, in our case, we're going to mess with velocities, which will be stored in volumes, taking the same space as our density. But velocities are stored as vectors, and we're going to see that in a minute. So here is our simulation so far. An empty object and a solver with nothing to solve. We press play, and it does it. It's doing something, it's just not much. The blue bar that's growing is how many cache frames are available to us to review. So we can scrub quickly through it and see what we came up with, and of course there's nothing there. Once we change the simulation at all, this will go away.